This is a recording of a presentation delivered at ISOPE 2017 conference. Some participants who expressed interest in our work were not able to attend the original presentation. Therefore, I made this recording. So, yeah, my PhD is going to be over by the end of this year, if everything goes according to plan. And this PhD is part of a larger endeavor, researching these innovative offshore foundations, the monobuckets. I, for one, am researching the soil properties, the disturbed soil properties, which raise a lot of questions to our clients. One of the selling points of this new design is its ability to control inclination. You see, in sand, we can loosen up the soil by pulsating jets of pressurized water. In clays, we have these clay chambers, which act like a hydraulic piston if you stop the flow of water. So we can control inclination during installation, and that raises questions regarding disturbed soil states left after installation. And in addition, we have the standard problem of lifetime of a structure. Deformations accumulate during the whole lifetime of an offshore foundation. It is repeatedly disturbed and restabilized for 20 years during each storm, and the serviceability limits are very strict. Half a degree of inclination can be accumulated in 20 years. We need to include drained component for static loads and undrained component for impact loads which are too fast for pore pressures to dissipate. And then we know from measurements, that full-scale measurements, that stiffness of these piles as well as monobuckets, stiffness is lost and recovered episodically with each extreme event, with each storm. And it all happens during regular loading. So it would be nice to have a testing method which allows us to observe the full picture, the big picture, all during irregular loading. And we argue that a frictionless triaxial apparatus is capable of delivering some of these solutions. A preview of the conclusion of this presentation. You see drained cycles, irregular, different deformation amplitudes, and drained cycles and undrained all together during regular loading, all on one specimen. Such loading is unheard of, but we attempted it and it was a success. Two years ago in ISOPE 2015, we presented the first early attempts of exploring triaxial testing capabilities of frictionless triaxial apparatus. Notice, frictionless triaxial was introduced in the 60s by Bishop himself. Soon after introducing conventional triaxial, Bishop addressed the problem that conventional tests can contract and dilate at the same time. Thus, if you measure volumetric change externally, you will measure a mixture of both contraction and dilation, and the two cancel each other out, so the measurement is corrupt. And this is true before yielding, before shear rupture occurs, and when the shear rupture occurs, you have this very localized deformation due to very nonlinear stress field. And again, this part is dilating while the rest of it could be contracting. So Bishop, knowing this in the 60s, introduced frictionless triaxial, the concept and implementation of a lubricated frictionless triaxial apparatus. It has a polished end plates. It has a very small filter in the center instead of the whole area. There's a small filter in the very center. And the rest of the surface is polished glass with layers of soft latex and high viscosity lubricant. So the friction is nearly zero. And if you look here, we can compress and pull a specimen by 10% amplitude without causing shear rupture or bulging. So we can pull a specimen back to initial length after testing its ultimate yield strength, as well as testing ultimate yield strength more than once. In addition, during undrained testing, we can apply force cycles, and then while controlling the deformation, we can test the ultimate yield strength undrained, and then we can pull the specimen back to initial length. We have presented this in 2015. In addition, we can liquefy a specimen, and then we can test the undrained ultimate yield strength of a specimen which was fully liquefied to a large amplitude. And then after testing the ultimate undrained strength, we can pull the specimen back to initial length. Each time we approach the ultimate yield strength, it's a good idea to use deformation control, which means slowly pushing the piston. And in case of frictionless triaxial, it's the bottom that moves, so that's the only moving part. After noticing that we can pull undrained specimens back to initial length 2 years ago, we attempted to restore the initial stiffness of disturbed specimens. You can see here the black line shows a specimen loaded using force cycles, all undrained, then compressed beyond ultimate using deformation control, and the specimen is then pulled back to initial length, and at this point it is allowed to drain consolidate. We allow the excess pore pressure to escape. Once drainage is complete, no more volumetric change is visible, we close the valves and attempt to repeat the initial test. The specimen now is back at initial length, or actually even elongated to some extent. It's denser, but the stiffness is lower. You can see the stiffness curve of the red line is way below the initial black line. So the stiffness is much lower. And when we apply force cycles and when we test the ultimate strength, it is slightly higher than it was before. Notice higher density. Higher density leads to higher strength, but not stiffness. Stiffness and liquefaction resistance is not recovered. So we pull the specimen back to initial length again, tried drain consolidating again, and nothing happens. The specimen remains disturbed to a very similar state as it was before. You can see the green line follows almost exactly the line that was there before, even though this drain consolidation has increased density again, which can be detected by further increased strength. So strength is directly proportional to density, but stiffness is not. Stiffness and strength are not codependent, a very counterintuitive property of sand. Fourth time, before the force test, we applied some deformation cycles. You see the specimen was drained, and some random small amplitude deformation cycles were applied. After applying deformation cycles in drain mode, the stiffness curve has recovered. Drained deformation cycles have recovered stiffness, and as well they have increased density even further, which you can see manifest itself in this curve right here. So this left us with a question 2 years ago: what happens during drain deformation cycles? Why is draining alone insufficient to recover stiffness? And this year, 2017, we are experimenting with drain deformation cycles using a frictionless triaxial apparatus. When we apply large deformation amplitudes, 15%. We can apply 3 cycles in drain mode. And you can see that the second cycle forms a kind of a stiffness triangle, which connects the drained ultimate strength with the drained ultimate strength in extension. So ultimate strength in compression, ultimate strength in extension. And these characteristic points are positioned at the peaks of applied deformation, mobilized deformation. The same happens at smaller deformations. If 5% amplitude is applied, you can see the min and max points captured by Coulomb envelope. These points are connected with these converging curves of stiffness. So this recurring formation of stiffness triangles caught our attention, and we are not the first ones to generate a stiffness triangle. Previous researchers were looking at the volumetric response, ignoring the stiffness for some reason. What we did is different from existing observations because we look at the exit path after forming a triangle. So you see we can force the specimen to yield once, pull it back slightly, apply deformation cycles, allow a stiffness triangle to stabilize, all while ignoring the density increase. And then we test the exit path, yielding second time. You can see we are dilating out of this exit path. And then we unload and reload, yielding for the third time. So we can test ultimate yield strength more than once on one specimen. But the new scope of testing does not end with the option of yielding more than once at more than one density. We can stabilize these triangles at different amplitudes, all in one loading history. You see we stabilize at one amplitude, second amplitude, it stabilizes gradually, and then a third amplitude, very small one, almost elastic. Notice during this test the density of all 3 triangles is very similar at some point. However, the stiffness is all over the place. We have the highest and the lowest stiffness at the same density. Stiffness and density are not mutually codependent somehow. But stiffness is directly proportional to the deformation amplitude, or rather the loading history, deformation history. Large deformation amplitudes produce low stiffness, small deformation amplitudes produce high stiffness. So we can stretch and reposition the triangle by manipulating the deformation history. This allows us to say with confidence that stiffness has exclusively deformation-dependent properties, as it adapts to different deformation amplitudes with a very predictable converging pattern. In addition, we looked at stress dependencies. So if we stabilize a triangle within a fixed deformation amplitude, then we stop and pause, or rather pause, and increase confining pressure. The triangle remains stable, but the peak points change to the new position, still governed by the same Coulomb envelope, and the stable triangle remains stable while the stresses are changing. So disturbed solid states are not affected by the confining pressure. Then if we disturb the triangle by yielding out of it at the third confining pressure, and we do not allow the new triangle to stabilize, and the disturbed triangle is then exposed to changing confining pressure in drain mode, all drained. So a disturbed triangle remains disturbed when confining pressures are changing. So we can state with confidence that the height of the triangle adapts instantaneously to changing confining pressure, whereas the width or the length of the triangle adapts to a deformation history. Thus, the stiffness of drained soil has exclusively deformation-dependent properties and exclusively stress-dependent properties, and the two work together. After making these observations, we started looking for a way to normalize and use these newfound properties. So we came up with the idea of normalizing the stress amplitude within the stress angle, and that's the standard procedure for hardening soil models. The new part is fitting the hardening curves to stiffness triangles. We normalized a handful of triangles within the mobilized amplitudes for each triangle. And once you normalize these triangles by the stress angle and by the deformation which caused the triangle, you notice that all of the triangles have a kind of unique hardening path, normalized between 0 and 1 along the epsilon axis and between 0 and 1 along the stress angle axis. So if we use this, we can see that it looks something like this. And the premature unloading has a smooth transition from one stiffness path to another. And notice this is between 0 and 1. So this whole thing will be fitted within a deformation envelope following this algorithm, but the deformation envelope merely interpolates within Coulomb limits. You see this angle of stress is this here. So we are always within the stress limits, but the interpolation is made with respect to position within the deformation envelope. Now, this might seem a bit backwards from the conventional, but it's not new. It has been introduced in the 80s by Paul Jerome Yoder, and we are using this kinematic isotropic hardening deformation envelope to interpolate the stress states instead of a stress envelope. You could say we are using a stress envelope which is a line with the exact stress angle assigned to it. Paul Jerome Yoder has a very comprehensive explanation of the concept. He shows full derivation, implementation, and comparison of other methods with this one. And this is how the model performs. The three amplitudes that were shown before, you can see it fits the first triangle and the second one. Although the recovery rate is not captured precisely, it captures the very fact of recovery. And the third triangle. So this illustrates the potential of frictionless triaxial testing. By improving specimen durability the way that the frictionless triaxial does, we can observe how disturbed soil stiffness evolves. The key finding is the very ability to observe this. The fact we can capture some of it merely proves the value of tests of such nature. And the stiffness triangles normalized within a hardening curve, they perform quite robustly for various loading histories. Here you can see 6 loading scenarios, 5 of which were captured using the same isotropic kinematic hardening rules. So one set of variables calibrated for the deformation envelope can capture all of this. Drain cycles, disturbed, recovery, and again change in stiffness, drain cycles, undrained compressing, pulling back to initial length, second undrained compressing, and then a third drained loading sequence. It's not perfect. The model is merely here to prove that there are systematic features of soil which are observable using frictionless triaxial. Following the reflective cycle, a scientific method, if you will, we challenged the new model by looking at even more complex loading scenarios. In the introduction, I have presented the loading scenario shown here. So you can see these are the 3 amplitudes shown before, and the test did not end there. You can see it has drained, undrained, drain, undrained, drain, undrained, drained, undrained extension plus drained compression, and then drained cycles to failure. A very irregular, complex loading history, which travels through a large magnitude of densities, and the specimen is liquefied and restabilized many times. It reaches non-liquefiable density right here. As you can see here, the stiffness does not disappear while cyclic loading through the zero axis. So non-liquefiable stiffness and then dilating out of it, following the blue line here, and then liquefied, partially liquefied, pull and drain compression. Pull, reliquefaction, pull, reliquefaction, pull, and then drain compression. Very complex loading, and that was the key. We wanted to see how far can the frictionless triaxial apparatus test. And just to show that the new testing scope can reveal some valuable information, we show how the stiffness triangle behaves during this complex behavior. You can see the triangles are predicted. The undrained peak is captured quite well. The changes in stiffness are captured. And the one very interesting feature of this deformation envelope is that it converges to the same triangle as the soil does. Thus, the model calibrates itself each time deformation of constant amplitude is encountered. So notice, the more cycles of constant deformation are applied, the more precise the model becomes. It calibrates itself. And the significant part is the big picture. It captures the general tendencies, the fact that the stiffness is recovering or is lost, even though it doesn't capture the exact shape of each loop, it converges towards the correct one eventually. So these might seem like crazy experiments, and still old testing limits should not be applied to new equipment. Frictionless triaxial was introduced as a superior, improved testing method. Conventional apparatus causes premature failure of specimens, which makes it impossible to access disturbed soil stiffness observations. The frictionless apparatus preserves the specimen during very complex loading history. Thus, frictionless triaxial is able to reveal evolution of disturbed soil stiffness, which takes place during irregular loading cycles combining drained and undrained loading. And this approach of testing and questioning theory, it's the path that Terzaghi followed, it's the path that Coulomb followed. So we should never limit our equipment to stay within theoretical limits. The equipment must be used to cross into the unknown, to reach for the testing scope within which theoretical models collapse. In the presentation at the conference, this would be the time for questions and answers. But since I can't really take any live questions, I will just fill in this moment of silence with some more slides. So the frictionless triaxial apparatus does not require any special adjustments. In a way, the only difference from conventional triaxial is use of frictionless end plates, which is polished glass with a small filter in the center. So on the polished glass we have vacuum grease, soft latex, vacuum grease again, and soft latex again. So there's a sandwich of lubricated latex layers on top of a polished surface, very low friction. And the construction of frictionless apparatus is described quite throughoutly in the literature, so there's no point in spending much time on that. And the model, the deformation envelope, is quite common outside the geotechnical paradigm. Outside the geotechnical paradigm, similar models are used for very basic applications, really. Pit controllers for hydraulic pistons and motors. These pit controllers, they adapt to plastic deformations without using plastic strains. This spring here is assumed, and if the real material deviates from it, the difference is simply added as an internal force. So this is very efficient because you don't need to convert stresses into strains. The algorithm is very efficient, especially with these curvatures which are present during cyclic loaded soil response. So you see, it uses even fewer steps than the conventional models do. This is very interesting for computational efficiency, as Paul Jerome Yoder noticed in 1980s. And the new tests could be of value when looking at near-field solutions in liquefied soil volumes. During earthquakes, the large volumes lose pore, thus sedimentation occurs. But near the buildings, we have localized liquefaction, which is driven by deformation. And there's a lot of research which supports this, especially work by Ricardo Dobry, even reaching as far back as the 80s, and he's been given awards of Seed Lecture, I think, some very, very high recognition rewards for his work describing liquefaction as a function of deformation. Then we have moving soil masses with shear tunnels and pipes leaving disturbed soil behind. So this disturbed soil will likely have lower stiffness, and you have seen how the model predicts loss and recovery of stiffness, the full circle of loss and recovery of disturbed soil stiffness. And so this new testing scope seems to be promising for bridging the gap between linear dynamics and nonlinear dynamics. we seem to have access to observations required to transition from somewhat stochastic linear dynamics towards deterministic nonlinear methods of solving irregular, loaded, disturbed sand response, all by using the frictionless triaxial instead of staying with the old standards. So thank you for viewing this presentation. If you have any questions or references we could or should follow, please do not hesitate to contact me, and I'm open for suggestions. I would be very happy to collaborate. Thank you.